16. Okay, chapter 16, it is talking about two different, I would say, physical quantities: temperature and heat. Here, just I want to maybe to focus on this difference. There is a difference between temperature and heat. They are not the same physical quantity. Although most of the people they are using them interchangeably, they are not. Okay, I will talk about the difference in a little bit. We will talk about temperature and the zeroth law of thermodynamics. We will also look at the thermal, it's like temperature scales, and talk about the differences, how we can convert from one quantity to another. We will talk also about thermal expansion, how materials they're gonna respond to changes in temperature. We are going to talk about the mechanical equivalent of heat and what does that mean. We are going to talk about specific heats, and we're going to see how really, why materials, different materials are really maybe reaching different temperatures when they are given the same amount of heat. And we will talk finally about transfer of heat with the different three methods: conduction, convection, and radiation. Now, definition of heat. Heat, it is the energy transferred between objects because of the temperature difference. Now, just here, I have my cup of coffee. It is, let's say, at 90 degrees Celsius, and my room is at 22 degrees Celsius. Okay, then there is a difference in temperature. You're gonna find that my cup of coffee is gonna give off heat. Okay, and this is one form of energy that is gonna be given to, the environment till we reach what we reach equilibrium. Thermal, we call it thermal equilibrium, when the two temperatures are the same. Now, when the transfer of heat between objects in thermal contact ceases, they are in what is called thermal equilibrium. There is a law called the zeroth law of thermodynamics. We are going to study different, let's say, laws here. All of them, they are easy. I will not say complicated, but the easiest one is like the zeroth law of thermodynamics, which is like we don't need even to give it a proof because it is really the common sense thing. If object A is in thermal equilibrium with object B and object C is in thermal equilibrium with object B, then objects A and C will be in thermal equilibrium if brought into thermal contact. That is, temperature is the only factor that determines whether two objects are in thermal contact or are in thermal equilibrium or not. Then the temperature, when they are going to reach that same temperature, they are going to be in thermal equilibrium. Now, A and B, no heat flows. Well, then we can say that A is in thermal equilibrium with B, and then also we know about B and C that there is no heat flow, which means C is in thermal equilibrium with B. Then I can say that A and C, they are at the same temperature, or they are in thermal equilibrium because no heat flows. Now, different countries, they use different scales for temperature. I will say most of the countries, they are using the Celsius scale, which uses like two fixed points. We call these fixed points. Water freezes at 0. Of course, we are talking about normal or standard pressure. Water boils at 100 Celsius. And for the Fahrenheit, which is an older system, water freezes at 32 Fahrenheit and boils at 212. And I know that this is our system here in the United States, but just here I want you to know that the scale here, it is actually divided into 100 degrees. Okay, and that one is 180 degrees. Okay, which means like the size of the Fahrenheit is smaller than the size of the Celsius, because both of them, they have the same I will say, distance between the two fixed temperatures. Therefore, when we will convert between Celsius and Fahrenheit, we need to consider that they are not equal, and we're gonna say the Fahrenheit is gonna be 9/5 times TC plus 32. Okay, I don't use usually more than one. This one is derived from this one, then no need for, like just it's enough to use this equation here. And if I have the Fahrenheit, I will put in the Fahrenheit number and get the Celsius. And if I got the Celsius, I'm gonna get the Fahrenheit. Okay, there is another quantity, and there was a big search for what is called like the absolute temperature, or like the absolute zero. Because remember, these like zero and the one that we have introduced, it is related to the fixed point where water freezes, or I will say water freezes, or when ice melts. Then and this is really, it was really a long search for that absolute zero. There is a documentary. Okay, I want to share with you just part of it, because I like to open your eyes on this one. It is really very interesting. And that one is the absolute zero. I don't know if I have saved that here. I should. Okay, or I'm gonna get it. But like it's actually it's a long one. Okay, but it's like 2 hours, I believe. But if you are fan of like these documentaries, it's good to, I will just maybe
When you support your local PBS station, you help make programs like this one possible.
The greatest triumph of civilization is often seen as our mastery of heat. Yet our conquest of cold is an equally epic journey, from dark beginnings to an ultra-cool frontier.
Yeah, this is
the lack of a universally accepted temperature scale.
There are all kinds of different ways of trying to stick numbers to these degrees of hot and cold, and they, on the whole, didn't agree with each other at all. So one guy in Florence makes one kind of thermometer, another guy in London makes a different kind, and they just don't even have the same scale. And so there was a lot of problem in trying to standardize thermometers.
The challenge was to find events in nature that always occur at the same temperature and make them fixed points. At the lower end of the scale, that might be ice, just as it begins to melt. At the upper end, it could be wax, heated to its melting point. The first temperature scale to be widely adopted was devised by Gabriel Daniel Fahrenheit, a gifted instrument maker who made thermometers for scientists and physicians across Europe. He had several fixed points. He used a mixture of ice, water, and salt for his 0 degrees, ice melting in water at 32 degrees, and for his upper fixed point, the temperature of the human body at 96 degrees, which is close to the modern value.
One of the things that Fahrenheit was able to achieve was to make thermometers quite small. And that he did by using mercury, as opposed to alcohol or air, which other people had used. And because mercury thermometers are compact, clearly if you're trying to use it for clinical purposes, you don't want some big thing sticking out of the patient. So the fact that he could make them small and convenient, that seems to be what made Fahrenheit so famous and so influential.
It was a Swedish astronomer, Anders Celsius, who came up with the idea of dividing the scale between two fixed points into 100 divisions.
The original scale used by Celsius was upside down. So he had the boiling point of water as 0 and the freezing point as 100. with numbers just continuing to increase as we go below freezing. And this is another little mystery in the history of the thermometer that we just don't know for sure. What was he thinking when he labeled it this way? And it was the botanist Linnaeus, who was then the president of the Swedish Academy, who after a few years said, well, we need to stop this nonsense, and inverted the scale to give us what we now call Celsius scale today.
Okay, then this is like if you wish to actually to look at this, and watch it, it's really very interesting. Now, as I said, there was a search for that absolute zero, and it was predicted by theory first. When like different scientists, they were really trying to understand the relation between pressure and temperature in Celsius. And they tried gas 1, gas 2, gas 3, and apparently, of course, there is a direct relationship between, pressure and temperature. And they all reach zero pressure at the same temperature, and that temperature was or is the negative 273.15. Then they predicted that this is gonna be the absolute zero, and then they tried like a different experiments and going back and forth, trying to reach this temperature in labs. Now the temperature scales, now we are having a third scale, which is called the Kelvin scale, which is the Kelvin, it is the standard unit for measuring temperature in the SI system, and therefore we know how to convert between Kelvins and Celsius. T Celsius plus 273.15 equals the Kelvin. Okay, then we use it even without the 1.5. Here are the three different temperature scales: the Fahrenheit, the Celsius, and the Kelvin, showing you different temperatures like the absolute zero, the boiling point of nitrogen when nitrogen is really boiling, when the freezing point of dry ice, the freezing point of water, and the boiling point of water, like different temperatures. Now, thermal expansion. Now, what if I am giving heat to, or I start warming a substance? Then most of substances, and said, maybe some of you're gonna say, oh, why most? It should be all. Expand when heated. The change in length or volume is proportional to the change in temperature. We're gonna understand why we said here most substances. Now, the proportionality constant is called the coefficient of linear expansion. That is, we are going to introduce. Now, the change in the length, then I will say if I have here a rod that has a length, I will ignore any area, like I will just consider that it has one dimension, L. And then I start warming it to temperature T2 or T final. Then I will have this L plus delta L, like its length is gonna change by delta L. And we did find that delta L, it has to do with alpha. Now alpha, it is called the coefficient of linear expansion. L0, and it has units of per degree Celsius or per degree Kelvin. L0, it is the original length, and it has units of meters. And delta T, I want you to know that delta T always is going to be change in temperature. Then it's going to be always final minus initial. Don't use like Ti minus T final. In this table here, we are listing some of typical values for coefficients of thermal expansion for lead, aluminum, brass, copper, iron, concrete, window glass, Pyrex glass, quartz. And I want you to know that these numbers are very important when we are using any material for any, for any construction or for any application in the life around us. One thing that I want you to pay attention to, the difference between the two glasses here. Pyrex glass, the one that you are using in chemistry labs, the test tubes, and like even we have it in cookware, like some of the, maybe bands or stuff we're using, they are made of Pyrex glass. And you can see that it is really slowly expanding, whereas the window glass, it's 11, then there is a difference. There is a piece of metal that we are using called bimetallic strip, and when we say bi means two, and it is two metals of different coefficients of thermal expansion, and it will bend when it is heated or cooled. It depends on what, like if it is higher temperature or lower temperature. Now, this piece, which is called the bimetallic strip, it is widely used in electric circuit where we are going to insert it, and then like it's going to be in a circuit, and then when it is going to be, let's say, your iron machine, and then you are going to have that warming, then it will bend and it will open the circuit, which means the current will not go through, and then your ironing machine will stop. Now, your ironing machine is not gonna start heating till it's forever or till it reaches infinity temperature. No, it will start, after a while it will stop, because the thermostat means like regulation of temperature. Okay, now also we can have expansion in area, and again delta A equals delta two alphas, because we have, let's say, length and width times the area times the delta T, which is the difference in temperatures. Holes expand as well, right? Because we're gonna find that they are going to, increase their diameter. Here, we are talking about a steel, and when they are going to name a substance for you, then they want you to use that, let's say, coefficient of linear expansion. The steel bed of a suspension bridge is 200 meters long at 20 degrees Celsius. If the extremes of temperature to which might be exposed are negative 30 to plus 40, how much will it expand and contract? Then here, and this is usually, actually this question is reflecting what we are doing when we are building bridges and when we are building, let's say, roads and stuff, because we are looking at what we have as ranges of temperature, and we're gonna find what is really maybe the needed. Sometimes we are going to put like spaces between the blocks so that when they expand, they will not buckle on top of each other. Okay, for the expansion, we did calculate delta L, and this is alpha times L0 times 40 minus 20. And for the second one, for the contraction, it is delta L is gonna come to be negative. Then the total range is gonna be 16.8 centimeters. Then this is the range, and then we need to compensate for that. Also, there is a change in volume when the solid is really warmed up. If we have a solid, we can say it's 3 alpha. If we are talking about liquids and gases, we replace alpha with 3 alphas with beta, okay? And again, it is the same idea, delta V, beta V times delta T. We call it bulk, we call it the beta. We are call it coefficient of volume expansion beta. Now, remember we said most of the materials or most of substances. Here is an exception, which is water between 0 and 4. Okay, then water between 0 and 4, it doesn't follow the expected behavior. It will reach the maximum density, which is 1,000 kilograms per cubic meter at, at 4 degrees Celsius. Now, it will expand when it is heated, but when it is close to freezing, it is actually expanding. And we have many things in life when, like, talking about this, like you can have your soda in bottle inside the freezer, and you will see it will expand. Sometimes it will push the cap, and then it will create a mess. The 70-liter steel gas tank of a car is filled to the top with gasoline at 20 degrees Celsius. The car sits in the sun and the tank reaches a temperature of 40 degrees Celsius. How much gasoline do you expect to overflow from the tank? Then here we did do the delta V equals beta V0 times delta T. Now here we have two expansions. One of them is going to be for the gas and the other one for the tank. Then we will calculate what is delta V first. And this one, the first one, it is going to be, the first one, it is, the first one, it's going to be in the gas, and the second one is going to be in the tank. And I will say the gas is the what did I say? This is, as I said, this is the gas and this is the steel. And we will find that, delta V for the gas is going to be 1.3, for the steel is going to be 0.05. So there is almost no expansion of the tank, like there is very negligible. And I will say some of the people, they're going to save money when they're going to fill the tank when it is cold. More gas molecules for the same price. All right, I'm going to stop here so that I will divide the chapter maybe into two recordings. Thank you.